When we think about higher derivatives, they work as you'd expect them to work, right? We can use higher derivatives basically by applying this process of differentiation repeatedly. And we could probably actually do it indefinitely where kind of functions allow us. So what I mean by that is if you had, for example, y equals to x squared, right? The first derivative, that would be y dash is equal to 2x. Now, if we want to find the second derivative, things to note, like from a notation perspective, we're not very creative mathematicians, we just add another dash to indicate the second derivative. And then we get to 2, and then if you want to do the third derivative, no surprises here, we add a third dash, right? And then what happens when you take the derivative of a constant? Well, you just get 0. And so what I mean by where functions allow us, like you could, I guess, keep taking the derivative of this, but you would just keep getting 0, right? So there's not much meaning or purpose to that. So that's from a perspective of like, why do we want to do that? Now, we generally focus on the second and third derivatives in this course, and that's because when we look at concepts of what the derivative represents, it represents the rate of change, right? So if you take, for example, for those of you who study physics, you'll be familiar with the concept of displacement. Now, displacement is similar to distance, but it's has some element of direction. So, for example, if I'm here and I go, units to the left, this is actually in the negative direction, we say. Okay. Now, when I differentiate displacement, when I think about the rate of change, we end up with something called velocity, and we often call this speed with direction, right? And if you think about differentiating again, if you went another time, well, if this is already the rate of change, and you want to find the rate at which that is changing, well, that's something called acceleration, right? So all of these three concepts are related to each other by deriving. And so that's why we're actually interested in taking the derivatives further than just the first derivative, right? So we've got the first derivative and then the second derivative. And we could keep going, depending on what function that we have. Okay, so that's the kind of concept behind it. I do want to mention something about notation though, because this is not the only notation you've used to represent derivatives, right? You have some other ones. So for example, dy dx, right? That's your first derivative. Now what would the second derivative look like? Well, that's a little bit different. It actually looks like this. I guess you could say it as d squared y, or we say d2y dx squared. But that's a different type of notation, and thanks, Maylin. We've got a few different notations here. We've got our first principles. There's your dy dx notation, and your f dash of x notation. So that's kind of similar to this one. This is your first derivative, your second derivative, which will look like this, right? We don't talk about that one. Got oh yeah, got a nice little meme there for you. Hope you guys like that. Sweet. All right, let's get rid of that. I just changed some examples around there, but let's do this one first, I think. Is probably a better start. So I want to find the first three derivatives of this expression here. So if I've got y is equal to x cubed minus 4x squared plus 3x minus 2, how do I find the derivative of this? Well, again, using your parallels, the great thing about this is they're all separated by addition and subtraction. So when that happens, what you can do is you can treat each of these as separate terms and differentiate them separately, which makes it nice. So let's do the first derivative. That would be dropping this power down. We get 3x squared because we're reducing the power by 1. Now, if there's constants there already, remember we keep them there, and we're going to multiply by this new power there. So we're going to drop the power down. There would be a 2 there, but we're going to multiply those two together. So 4 times 2, and that would be 8. X to the power 1, I'll leave that power there just to know that it's been reduced, plus 3, because when you just have 3x and you differentiate it, that just becomes 3, and our constants, they go away, becomes 0, right? So now we've got 3x squared minus 8x plus 3. What about the second derivative, right? Well, second derivative, same idea, right? We're dropping this power down now, so we're dropping the 2 down here, but there's already 3 there, so we'll multiply those two together, and we'll get 6x to the power 1, because we're reducing this by 1, this power here. And then again, we've got 8x here, so that's just going to become 8. And then the plus 3, poof, goes away. All right, get rid of that one there, we don't need that. Lucky loss, third derivative. Again, this is quite nice now because we just have two terms we have to differentiate. 6x, that's just going to become 6, and then negative 8, that goes to 0. So you can see beyond this point, if you were to keep dividing, you would just end up with zeros multiple times, so you have over here. So not much more point in doing that, right? It becomes a little trickier when you have things like part 2 now. So here you have to use chain rule. And with chain rule, remember, there's a few things we have to consider. Firstly, you have to think about, okay, what's the expression inside the brackets? So that's 2x plus 5. And you also have to think about the power that's outside here, right? So for the first derivative, we're going to have to drop this power down. That becomes coefficient at the front. And we've got 2x plus 5. That stays the same. Now we're going to reduce this power by 1. But then we also have to multiply by the derivative of the inside expression here, right? So we have to derive this part. And so that would just be 2. And so when you put that together, you're going to get 14. So 7 times 2, that's 14 outside of 2x plus 5, all to the power 6. Okay? That's the first derivative. Now with the second derivative, like I mentioned with the notation, we are a bit uninspired here. We just add another dash to indicate the second derivative. And we're going to approach this in a similar way, just being aware that there's a constant at the front now. So what are we thinking, right? You can pause the video and have a try yourself. But when we look at this, we just want to apply the same process, reducing this power by 1, and then dropping, well, maybe I should drop the coefficient out there to before. So let's do that. You know what? Let's just do that again. So for the second derivative, we can apply the same process. We can drop the power down, multiply it by 14. I can't do that in my head right now. Reduce this power by 1, and then still multiply by the derivative of the inside, which has stayed the same. So by my calculations, this looks like it's going to be 84 times 168. Do I have a calculator? Okay, I should just trust myself, right? So 168 outside of 2x plus 5 all to the power of 5, okay? So that's the idea with higher derivatives, right? We can keep applying this process of differentiation as long as we're using the same rules as before, but we just have to tweak that notation slightly. So beyond that, I guess you might be thinking, okay, what kind of other questions can they ask? Well, because we can take derivatives now, we can also be asked to show things in relation to these derivatives, right? So for example, we've got one here, f of x is equal to 4 times cos 3 of x. And we want to show that f double dash of x is equal to negative 9 times f of x, right? So what's going on here? Let's break it down, right? Anytime we ever show that question, generally it's good to start from one side and end up to another. Another option is that you can find one of the sides, find the other side, and then show that they're the same. That's the option I'm going to do here because these are actually kind of different expressions. It's not necessarily easy to get from one to the other, right? So what I'm going to do is I'm going to say, what does negative 9 times f of x mean? Well, remember your notations, right? If you've got negative 9 outside the front here, you're just multiplying, right? So negative 9 of f of x, which is equal to negative 9 times 4 cos 3 of x. All right, now I'm just multiplying these two constants together. That would be negative 36. So I'm going to leave that there for a second, right? That's one part of the puzzle that I need. The other part is, what's f double dash of x? Well, I've seen that notation before. That's just the second derivative, right? So let's go to the first expression, f of x is 4 cos 3 of x. Now this is where you're going to have to remember your derivatives rules, and there's a few of them. So f dash of x, now when you derive cos, think back to what you need to do, you actually end up with negative sign. So when we apply this, so we also have to be aware of the function inside here, we have to take the derivative of that. So derivative of that is going to be 3. You can bring out the front. So a few pieces you have to think about here. We've got the negative, that 4 stays there. We've got this 3 component here, and it becomes our sine function, okay? So let's just recap that again. So I've got the constant that stays there. I've got the negative now that's introduced because I derive cos, which becomes negative sine, and this 3 has to come out the front because it's the derivative of that expression, and then I end up with negative 12 sine 3 of x. Can you see the last step I have to do? Deriving negative 12 sine 3 of x, right? Well, remember what happens when you derive sine, you end up with cos. So this expression, this constant rather, this is going to stay there. And when you derive it, you have to take the derivative of that inside component as well and bring it out. So we end up with negative 12 times 3 cos 3 of x, which, wait a minute, that suspiciously looks very similar to what we had up here. Okay, so that's the same as that. It's always nice to finish off with a concluding statement. So I'll just finish off with, therefore, sorry, I probably missed a thing here. That should say f double dash of x here, because I took the second derivative. My mistake. So let's go back up here. So now then I know that f double dash of x is equal to negative 9 f of x. Okay. All right, so this one's a bit trickier because now it involves that concept that I introduced just at the beginning of the fact that displacement, velocity, and acceleration are all related together. Okay, so let me just recap again. Right, displacement talks about where you are in relation to a point in time. Right, so I said, okay, maybe I'm like 5 meters from where I started, but we incorporate some direction as well. Like I'm 5 meters to the left or 5 meters to the right. Now, if you take the derivative of that, right, the first derivative, that's saying, okay, at what, remember, derivative also means the rate of change, right? So at what rate are you moving? So that's like your speed. But because we incorporate direction into it now, am I going in the left direction or the right direction? Then we call this a different term. It's called velocity. So we can think about that as speed with direction. And then the last thing to think about is, okay, what's the rate of change? So it's kind of like inception here, right? So I know I'm traveling at, for example, 5 kilometers per hour in the positive direction, right? But at what rate is your speed changing? Now, when you think about your speed changing, if you're driving a car, for example, right, how do you change your speed? Well, you put your foot on the accelerator, right? So as we accelerate in a particular direction, that determines the rate at which our speed is changing. So that's the second derivative, and that's called acceleration. What goes beyond? Well, why don't you try to find out for me? So find when the acceleration is 0. We need an expression for that. This is the displacement, so let's try and find the velocity and acceleration. And all we need to do is derive these, right? So v, that's how we can say that's velocity. If we derive these, we can apply our same principles. So 1 over 3, drop the power down, reduces power by 1. Same thing here, drop this power down here, reduces power by 1. And then here we'll get left with 27. Okay, let's simplify this out a bit. So we'll get t squared minus 12t plus 27. Not quite there, though. We want to find when the acceleration is 0, so we need to derive one more time. So the second derivative, so a is going to be equal to 2t minus 12. When we take the derivative of each of these separately, and 27, that's becomes 0. And so the question is now asking, find when the acceleration is 0. And so it should really say in the question, though, that t is time, let's say in minutes. So if t is time in minutes, and we want to find when the acceleration is 0, it's about looking at which parts you're given and which parts you want to find. We're told that a is 0, or we're asked to find when the acceleration is 0. So we let a equal to 0. And so we've created an equation here. 0 is equal to 2t minus 12. And so solving this, we put 12 to the other side. We get 2t is equal to 12. And so t is equal to 6. So when is the acceleration 0? Well, after 6 minutes. Because t is equal to 6, and we're using minutes as our units. Okay? That's a bit of a different question to get you thinking about when would we use these derivatives in an applied context. And they can ask you a whole range of other questions as well in relation to this. This is just a bit of a snapshot to get you started.